This entire book is about a new way of looking at nature. We often think that the world stays very calm and balanced, but the truth is that nature, the natural world, is always in a state where anything can happen at any time. The old rules of science say that the world should have been very simple. But we see that here there is life, history, and countless stories. The question is, when the world began with just tiny particles, how did it become so complex, so tangled up? The answer is hidden in a special rule called the self-organized condition, or self-organized criticality. This means that things present in nature bring themselves to a delicate turning point where even a small change can bring very great destruction. To understand this, let us look at a child's story. Suppose a child is sitting at the edge of the ocean and making a pile by dropping sand from his fist. In the beginning, the pile of sand is flat. Where you drop the sand, it stays right there. As the child adds more sand, the pile starts becoming taller and sharper. That is, steep. Now small bits of sand start slipping. A time comes when the pile becomes so tall that just one more grain added can make the whole pile collapse. This is called the avalanche of sand. When the pile becomes very tall, you cannot say which grain will topple the pile, and it works on its own will. The same thing happens in nature. Earthquakes or the complete extinction of an animal can often happen without any big reason. It is not necessary that some big rock fall from the sky. Just a small disturbance is enough. Nobody pushed this sand pile from outside. It reached that delicate condition on its own. This is very easy to understand. If you have a computer, you can investigate this yourself. No very big education is needed for this. Just school-level math is enough. Have you ever thought about why this world is so tangled up? Scientists say that nature works in a very special state, where everything keeps managing itself automatically. To understand this, we first need to know what complexity actually is. The rule is simple, but the world is complex. Since this world was created, since after the Big Bang, everything has been running according to the rules of physics. Scientists did a lot of research and found that the smallest things in the world, like atoms and particles, follow very straightforward rules. These rules of physics are so simple that they can be written on 2 pages of a notebook. Like Newton's rule says that if you push something, it will move forward. But when many things come together at once, calculation becomes very difficult. Scientists have always adopted the method of breaking the world down into small pieces to understand it. Simple system, that is, a plain system, like a piece of salt, that is, a crystal. In this, every grain is placed in the same line. This is easy to understand because it looks the same from everywhere. Then gas. This is also easy to understand because its grains collide with each other very little. When we open the window, we can see mountains, rivers, oceans, and earthquakes. Every place is different and changing every moment. This change and different appearance is what we call complexity. This complexity is not just limited to mountains. The brain inside our body and our society, that is our community, is also part of this. The human brain is perhaps the most tangled up, the most complex part in the world, the fabric of society. In this, things like financial matters, that is, the economy, government, and history are connected. So can we know everything in advance? No. In recent years, scientists have accepted that even with the help of computers, we cannot tell everything in advance. Like physics can tell how an apple falls down from a tree, but it cannot tell why Newton was watching that apple fall. In nature, things keep joining on top of each other automatically, like chemistry was formed from physics. Life, that is, life and biology, was formed from chemistry. And then society and the economy were formed. All these things were not made by anyone from outside. Rather, they came out on their own because of the small parts working with each other. So how do so many different things run by the same rule? To solve this puzzle, scientists have started a new kind of investigation. In physics, we can tell in advance what is going to happen, and then check it in the lab. But there are very many places in the world where this method doesn't work. A famous writer named Stephen Jay Gould asked a big question in his book. He said, "How do scientists explain things that happen in history only one time? Like the formation of the world, the history of rocks, or the evolution of animals. We cannot redo all of these in a lab and see." Gould says that here science has to work like a story. In evolution, that is, development, or history, that is, history, we cannot do experiments, because here nothing happens exactly the same way again. We can only see what happened in the past, but we cannot tell what will happen in the future. That is why science has been divided into two parts. First, hard science, like physics and chemistry. Here, math formulas work, and you can tell for certain what will happen. Then there is soft science, like history, biology, and economics. Here, only stories work. In history, a small event changes everything. This is called coincidence. If we play the film of history again, the result will be different every time. Think, if Columbus's parents had never met, or Columbus had never been born, or if the weather had been bad that day, then America would never have been discovered. History would have been completely changed. History cannot be told in advance. But when it happens, it can be explained like a story. If we cannot tell anything certain about tomorrow, then what is the benefit of such science? The truth is that this theory will not tell you whether an elephant will be born tomorrow or not. It is very deep, very abstract. It only explains how changes happen and why there are so many kinds of things in the world. This theory works on a special method which we call statistics, or the game of numbers. It tells not about one single thing, but about the whole crowd. The problem is that we humans don't just want numbers. We don't just want data. We are concerned with ourselves. People want science to tell them when the stock market will go up so that they can make money. We are not concerned with how many earthquakes come on average in a year. We just want to know when an earthquake will come under our house. But nature doesn't work like that. It is made up of very many small coincidences. Like the extinction of dinosaurs was a coincidence, because of which we, that is humans, got a place to flourish. The next time you look at this world, remember that this is not a machine whose calculation can be done. Rather, it is a never-ending story. We all think that our story is completely unique. We find it very difficult to accept that our life is just one in millions and billions of coincidences. The difficulty is that we don't have another world to compare our world with. When something will happen in life cannot be told in advance. So then, what does this complex science, or the science of complexity, teach us? In reality, there are some things in nature that look the same everywhere, like great destructions, special designs, that is, fractals, and strange noise. Why do these things happen everywhere? This is the real work of science. Destruction always comes in a simple way. This is just like the domino effect, where one thing falls and it brings down many other things with it. The cracks inside the Earth spread in the same way and bring very powerful earthquakes. Scientists saw that there is a straight calculation for earthquakes coming. There is a simple rule. If somewhere 1,000 small earthquakes of magnitude 4 come, then there will be 100 of slightly bigger magnitude 5 and 10 of even bigger magnitude 6 earthquakes. This works like a straight line. This means that big earthquakes are nothing separate or unique. They also run by the same rule by which small earthquakes run. So we should not change our way of thinking separately, only for big accidents. Rather, we should find a rule that can explain all. The same is true in financial matters. In 1966, a scientist investigated the prices of cotton. He saw that the falling or rising of prices also follows a fixed rule, just like earthquakes. A sudden fall in the market crash, is not a coincidence. People may call it a strange situation, but the truth is that big changes are also part of the same rule by which daily small changes happen. Here, no change is special. All are connected by the same thread. This same thing applies to the world of living beings. That is, biology. Millions of years ago, dinosaurs became extinct. We think this was some very big and separate event. But if we look at the record of the past 600 million years, we find that the dying of living beings has been moving at a fixed pace. Sometimes few beings die, and sometimes very many. The extinction of dinosaurs was also a part of this big record. This means whether it is an earthquake, financial ups and downs, or the extinction of beings. Nature works the same way everywhere. Big and small accidents are weighed on the same scale. When big events will happen, there is a probability, an expectation. But this does not mean that they will come at a fixed time. This is just like the game of gambling. If red has come 7 times, it does not mean that black will come next time. Next time, also there remains only a 50% chance. People of old times thought that the world changes very slowly. This was called the slow method, or gradualism, by which mountains are formed slowly over thousands of years. But the catastrophic thinking, that is, catastrophism, says that changes in the world come through sudden and great destruction. Scientists earlier did not believe this. But the truth is that sudden big blasts and changes keep happening in nature. A man named Mandelbrot found a new word, fractal. This is a design that looks the same at every size, like the Norwegian coastline. If you look at its map, it is crooked and winding. If you look at it more closely, if you zoom in, it will again look the same, crooked and winding. It has no single size. Mountains, clouds, and even the universe are made of this same fractal design. No cloud is of the correct size. They look the same at every size. Just as there are designs in space, similarly in time, also there is a special kind of noise or signal. This is called 1/f. This signal is found everywhere. The ups and downs of river water, the traffic of vehicles on roads, and even in our music. If a sound is very plain, then it seems boring. If it is completely like noise, then it also doesn't feel good. But the 1/f sound feels natural to listen to. That's why we like music. In human-made societies, people's society, also a strange rule works. This is called Zipf's law. If you look at the population of cities of the world, a few cities are very big, and many cities are small. Its graph always forms like a straight line. If you count the words in a book, the most used words like "thean" and always come in a special count, a special frequency. whether the book is a newspaper or the Bible. This rule never changes. In mathematics, when we see a straight line on a graph, it is called a power law. Its meaning is very simple. In nature, things look the same at every size. Whether you look at a small part of Norway's coast or a very big coastline, their design will seem the same. In this, no part shines separately. All run by the same rule. Scientists believe that things that are completely in balance don't do anything special, like sand lying on a flat beach. If you move a grain of sand there, only that will move. The rest of the pile will not be affected. In such calm things, neither does any great destruction come, nor does any unique design, that is, fractal form. In old times, people thought that financial matters and society also remain in such a balance. But if everything were in balance, then why would there be a sudden fall in the stock market? The truth is that nature runs not with calm, but with sudden big changes. This is called an explosion in the middle of calm, or punctuated equilibrium. Around 1980, scientists learned a lot about chaos, like a swing that is pushed again and again, where it will be and when becomes impossible to tell. But remember, chaos does not mean complexity. Chaos is like the white noise, useless noise that comes on radio. Completely random and boring, whereas complexity is like music. Like music, there is a rule in it, but nobody knows what turn it will take when. Now let us understand the real thing. In nature, everything, whether it is an earthquake or the evolution of living beings, their development, slowly brings itself to such a delicate state where anything can happen at any time. To understand this, remember the sandpile again. The sandpile slowly gets taller. It reaches a state where it is very delicate, that is, unstable. Just adding one small grain can make the whole pile collapse. Nobody pushed this pile from outside. It brought itself to this state, this self-organized state. Nature works the same way. A small event can bring very great destruction. If this way of thinking, this mindset is correct, then we should accept that big destruction in history, financial matters, and society cannot be stopped by anyone. This is the rule of nature. Big accidents and the small events that happen daily are both produced in the same way. The extinction of dinosaurs was also part of this rule. In 1987, Chow Tang, Kurt Weisenfeld, and I made a very simple method. We called this the rule of the sandpile, or the sandpile model. From this rule, we found out how small things bring themselves to such a delicate state where instead of changing slowly, they work like sudden explosions. The funny thing is that we had not started working to study sandpiles. Like many great discoveries in science, this also just happened suddenly. We were working at Brookhaven National Laboratory. This is a very big government place near New York City, where approximately 3,000 people work. This place is famous for its great discoveries. Here there are very big machines that investigate the world's smallest, millions of the smallest particles. Many scientists here have also received big awards, that is, Nobel Prizes. I came here for the first time in 1974. I worked here on things that could take electricity from one place to another without any obstruction. Here I understood that when very many particles come together, they start working in a special method, a special pattern. After being away for some years, I came back here again in 1983. Our group was very small, but we had the freedom to do the work we liked. Often people think that for a great discovery, millions of dollars and big machines are needed. But the truth is that today's great ideas often come from a small team of 1 or 2 people. We were busy solving a puzzle, which is called 1/f noise, or 1/f noise. This is a type of signal that is found everywhere in nature, whether it be the light of stars or the level of river water. We found this noise very strange because no simple rule could explain it. We thought that this can only happen when many parts of a large system are working together. Like the ups and downs of the Nile River, water is not just a matter of water, but it is connected to the entire weather of Africa and the land there. At the end of 1986, Susan Coppersmith came to meet us. She told us about a new way of movement of electrical particles, that is, charges. She had given a very interesting idea, which she used the story of a dog to explain. This is where our thinking got a new direction. Suppose there is a stubborn dog that doesn't want to move forward. It is being pulled on a rough road with a rubber leash. In the road there are many small hills and ditches, bumps and valleys. When the dog is pulled, it slips from one hill and jumps to another. Now here a funny thing happens, because the leash is still being pulled. After jumping, the dog doesn't fall to the very bottom of the ditch. It gets stuck somewhere near the top of the other hill. That dog keeps sitting near the top until the pull of the leash increases so much that it overcomes the dog's friction. Then the dog makes another jump. The lesson here is that the dog was sitting near the top, so it is in a very weak balance. Even a small push can make it fall down. Things that are in calm, that is, equilibrium, always rest at the bottom of the ditch. But things that work with outside force are always hanging near the top. Scientists tried another method to understand this. They took many pendulums and connected them to each other with the help of springs. On the computer, they made a grid, a web where every pendulum was connected to its neighbors. They gave a sudden push to any one pendulum so that it made one complete revolution. Because all were connected to each other. One spinning caused tension in the spring, and it forced its neighbors to spin too. This was just like spinning something in honey or syrup. As soon as you stop pushing, because of friction, everything stops. From this investigation, we understood how things in the world put pressure on each other. People often ask, why do you use simple things like pendulums or dogs to understand nature? Why not investigate the real world? The answer to this is very straightforward. We cannot put the real world inside a computer. Think, if you want to understand biology, can you put a real frog inside a computer? No. You can only make a picture or model of it. The way scientists think is something like this. If we want to understand how life moves forward, we don't need to know how babies are born or how DNA works. That is, remove the unnecessary things. Then there is the backbone. We remove everything until only the real bone or skeleton is left. We believe that whether there is an earthquake in the world or it is a financial matter, all run by the same big rules. In old times, a scientist made a rule. That rule was very simple, like a cartoon's map. People laughed that how can such a simple rule explain the real world? But later, when investigation was done, it was found that that simple rule fit exactly on water waves and the movement of swings. To understand this, listen to a fun story. Once a farmer asked a scientist for help as to how his cow could give more milk. The scientist stayed absent for many days and then suddenly came out very happy. He made a circle on the blackboard and said, "Suppose our cow is like a round football." Everyone was left amazed. But scientists' way of thinking is just this. They first make things completely simple so that the real rule can be understood. We did the same. We took many pendulums and laid them out like a grid. We kept pushing them in the same direction. Slowly, energy started accumulating inside them. A time came when they became so unstable, so delicate, that just pushing one pendulum caused many pendulums to spin together. This can be called an avalanche, or a type of destruction. This was just like dominoes falling one after another. On the computer, we saw that sometimes only 1 or 2 pendulums spun, sometimes a few more, and sometimes the entire grid started dancing. When we made a graph of this, we found a very great thing. Small accidents were very many, and big accidents were fewer. When we put this on paper, it formed a straight line. This is called the power law. This means that our pendulums were working exactly the same way as real earthquakes come in the world. The most surprising thing in this entire research was that we had not tuned, that is, tuned the pendulums. They had brought themselves, that is, self-organized, to that delicate state, that critical state. Like in a nuclear reactor, humans have to set machines so that an explosion doesn't happen. Here, there was nothing like that. Here, nature did its own work. This is what we call the self-managing delicate condition, or self-organized criticality. It seems like some invisible hand is managing everything and has brought the world to that turning point where, with even a small push, anything can happen. Suppose there is an empty table and you are slowly dropping sand grains on it one by one. In the beginning, the table is flat, that is, level. Where you drop the grain, it stays there. We call this equilibrium, or the state of calm. Nothing special happens here. As you add more sand, the pile starts becoming taller and sharper, that is, steep. Now, sometimes dropping one grain causes small bits of sand to start slipping. But this slipping only happens in the same place where the grain fell. The other parts of the pile are not concerned with this. Then a time comes when the pile becomes so tall that it cannot become any taller. Or now, however many grains you drop from the top, on average that many grains will fall off the edges of the table below. We call this the self-managing delicate condition. Now the whole pile has become one. Now wherever a grain falls, it can cause a disturbance in the whole pile and can bring very great destruction. The best thing about this method is that it knows how to manage itself. If you add wet sand, which has more friction, in the beginning the pile will become taller. But in the end, it will again reach that same delicate state, that same critical state, from where it will start falling. If you add dry sand, the pile will be a little smaller, but it will again come to that same delicate turning point. Whatever you do, the pile always brings itself to that state where even a small push can bring great destruction. Scientists made very simple rules to understand this on the computer. Suppose the table is divided into squares, like graph paper. You add grains of sand to each square. If any one square gets 4 grains, that square becomes unstable. That square gives its 4 grains, 1 each, to its neighbors. Above, below, right, and left. Now think. If those neighbors already had 3 grains, then they will also become 4. And they will also share their grains. This is what we call an avalanche, or the chain reaction of destruction. A scientist named Per Bak illustrated this with a fun story. Think there is a very big office. Here, many clerks, that is bureaucrats, are sitting at their desks. The rule is that whenever any clerk's desk has too many papers piled up, instead of doing his own work, he passes one paper each to all 4 of his neighbors. In the beginning, everything remains calm, but when the office fills up with papers, just one new paper coming can create chaos in the whole office. Millions of papers will start moving from here to there. We can call this the destruction of the office, or a bureaucratic catastrophe. Mandelbrot had created the word fractal, but he didn't tell how these designs are made. How are these fractals formed? An experiment from Hungary showed that these designs, fractals, are actually formed because of great destruction. We think that mountains and landscapes are standing still in one place, but in reality, they are slowly changing. Earlier scientists thought that earthquakes and cracks in the earth are different things. But the truth is, they are 2 sides of the same coin. Does the sandpile rule also work in nature, in the natural world? David Noeva investigated the soil and rocks falling on the mountains of the Himalayas. On the roads of Nepal, he saw that from a shovel full of soil falling to a very large mountain sliding. Everything follows the same rule, that is, the power law. Small accidents perhaps did not have a complete record kept, but big accidents clearly showed that mountains are also in this delicate state, that is, critical state. The soil that collects on the seashore turns into stone in layers. Sometimes the slope inside the ocean wobbles, and a very large flow of mud comes. This is called a turbidite. Scientists from Lamont Doherty investigated these millions of years old layers in Death Valley, California. They found that the thickness of these layers also follows the same rule, that is, the power law. This is the evidence that rocks are also made from this same process of destruction. Landscapes are very complex. Every place is different from another. Scientists Donald Turcotte and Andrea Rinaldo worked on this. Rinaldo saw that the way rivers connect with each other, their method also follows a rule called Horton's law. They made a model on the computer. In it, they showed that when land rises up and water cuts through it, that delicate condition forms automatically. The rivers and mountains that formed from this looked exactly like the real world. This shows that our landscapes, that is, our scenery, is also part of this delicate game. This is not a math game, but the real truth of nature. These special rules work not only on our Earth, but in the entire universe. A pulsar is a star that spins very fast. Sometimes its spinning speed suddenly changes. We call this a jolt or a glitch. Scientists investigated this for 25 years. They found that these jolts also follow the same rule by which earthquakes come on Earth. In reality, these are earthquakes of stars. On a pulsar, there is a lot of pressure of gravity, that is, gravitational force. When this pressure increases very much, the outer layer of the star, that is the crust, breaks and falls. This suddenly increases the speed of the star. This is exactly like how an ice dancer spinning gathers her arms and spins faster. A black hole is a thing in space from where even light cannot come out. Scientists from Japan told that a black hole also works like a sandpile. Gas particles fall in from all around it from outside. When too much gas accumulates, it falls inward all at once. This releases X-ray light, which we can see from Earth. All of this is also part of the same self-managing rule. We don't need to go very far. The same happens in our sun. Flares, that is, flares, keep coming out of the sun all the time. Most flares are small, but sometimes very big flares come out that ruin the signals of our radios and phones. The count of these flares also follows the same straight line, the same power law. When the magnetic force, that is the magnetic power, inside the sun has a disturbance, it suddenly breaks and makes an explosion. This is exactly like how one grain of sand falling brings very great destruction. When scientists investigated this, they found that the sun also works in that delicate state. That is, the critical state. Now we will talk about the most tangled up thing, and that is life. In the beginning, scientists had not thought about this, but now we know that life also runs by this rule. To understand this, scientists made a simple method called the game of life, a model. This is like a grid, a web of boxes. In this, there are some simple rules for every box. Like if a box has too many neighbors, then it dies, and if it has few, then it stays alive. Scientists like Stephen Wolfram showed how these very simple rules can make very big and tangled up designs in very little time. This entirely teaches us how small things coming together can make a very big and intelligent world. Stephen Wolfram did not make any big theory about these machine rules. Later, he left science and made his own software company. His thinking was, what will be the result of some rules? You cannot tell without running it on a computer. But scientists have their own methods of estimating, by which they understand what is going on inside. Compared to a straight line, a two-dimensional grid world is even more interesting. In this, a box has 8 neighbors all around. In this world, there can be so many rules that writing them is not possible. The computer also cannot check all of them. Many years ago, a mathematician named John Conway chose one from these hundreds of millions of rules and named it the game of life. He was looking for a simple method of how society and people are formed. This game showed how from very simple local rules, very tangled up, very complex worlds can be formed. The rules of this game are very simple. If a being has more than 3 neighbors around it, then it dies from overcrowding. If it has only 1 or no neighbor, then it dies from loneliness. A new being is born in an empty space, only when it has exactly 3 neighbors. From these simple rules, such things were formed that are amazing to see. Glider. This is a shape. This is a shape that keeps moving diagonally on the grid. That is the web, until it hits something. Then blinker. These keep flickering in their own place. Then glider gun. This is like a factory that keeps making new gliders and sending them out. At Brookhaven Lab, we scientists investigated this game. We wanted to understand what is so special about the rules that Conway chose. We started the game and let it run until everything became calm. Then we made a small change in it. That is, we removed a being from somewhere or added a new one. This was just like adding a new grain to a sand pile. This small change started a chain reaction. Sometimes few beings died and were born, and sometimes very big explosions happened. We did this millions of times, and when we made a graph, we again found the same straight line. That is, the power law. This means that the game of life also works on the same self-managing delicate condition. That is, self-organized criticality. Scientists from around the world checked millions of rules, but no one found another rule like the game of life. This means that John Conway had perhaps unknowingly set this rule exactly at that delicate turning point from where life and complexity are born. The lesson to learn is that if the rules have too much chaos, that is, chaotic, then everything will become like noise. If the rules are too slow, everything subcritical, then everything will freeze and become boring. Only in the delicate state, that is, criticality, can the world experiment with new things. We think that there is a very big difference between lifeless things and living beings. But who knows? Maybe it is not so. Perhaps the same rules that manage mountains and earthquakes also run the evolution, that is, the changes of life. If someone had been there when life began, perhaps nothing would seem strange to them. They would only see that work among small chemicals is increasing, and they are slowly becoming more complex. Life's beginning would not have been from something as complex as DNA. DNA is the result of a very long evolution, that is, change. Perhaps from astrophysics to geophysics, and then to biology, everything is connected by one thread. All of this is part of the self-managing delicate game, that is, the self-organized critical process. Just as in a sand pile, millions of grains are connected to each other. Similarly, in life, also millions of beings work with each other. In New Mexico, there is a place called the Santa Fe Institute. Here, thinkers, that is, thinkers from around the world come together. This is a place where a doctor can sit and talk with a financial matters expert. Here, every day, new ideas are discussed. Usually, scientists want to understand the world by breaking it into small pieces. This is also called the method of reducing, or reductionism. But this institute is different. Its belief is that whether they are physics particles, biocells, or market buyers, the way all of these work can be the same. In the year 1989, a scientist, Stuart Kaufman, told me a wonderful thing. He said that the change of life does not happen slowly, but in stops and starts, like explosions. This is called paused calm or punctuated equilibrium. What happens is that for a very long time, nothing changes. Stasis remains, and then suddenly an explosion happens in which many old beings are finished and new beings are born. This is just like our sandpile. For a long time, nothing happens. Then one grain falls and changes everything. When we looked at the evidence of the history of life, we found that it also follows the same rule. We call this the power law. This means that life also works in the self-managing delicate state. Scientist Sewell Wright had made a map to understand life. Every being's power to stay alive and produce children is called fitness. Consider this like a hilly area. High peaks, these are the places where beings are most fit and happy. Low ditches, that is, valleys. Here beings are weak. Every being tries to climb the hill through its changes. If it makes some change by which it becomes stronger, it goes up. If the change is bad, then it falls down. Scientists of old times thought that life is just a race of always climbing up, but the truth is that this map itself also keeps shaking and changing. Darwin believed that life changes slowly and continuously, but his rules only talked about individual beings. Sewell Wright explained this like a map. He said that when a being reaches the top of the hill, it stops, and wherever it goes, it will only go down. Think, a land animal cannot grow wings overnight, for this many changes need to happen together, which is impossible. In this way, life should have frozen in one place, where there would be no change. But that didn't happen. Why? Stuart Kaufman explained where the shortcoming was. Scientists, that is, we, forgot that beings don't live alone. They affect each other. If a lion learns to run faster, then a deer's life is in danger. If a frog's tongue becomes sticky, then a fly has to make its feet slippery so that it can survive. This is called the Red Queen effect. It came from a story in Alice in Wonderland. Here, the Queen says, to stay in your place here, you also have to run as fast as you can run. Our world is a fast-paced place. Here, every being has to keep changing, even just to stay alive. Kaufman called this co-evolving mountains. When one being changes, the other being's mountain shakes, and it has to climb up again. To understand this complexity, Kaufman made a simple rule. He represented genes with the numbers 0 and 1. A change in a being means making someone 0 into 1 or 1 into 0. If this increases its power, its fitness increases, then the change is accepted. But here there is one more important thing called C. That is, how many other beings one being is connected to. If beings are less connected to each other, then everything will quickly become calm. Everyone will sit on their small hill and not move forward. This is also called Nash equilibrium. If everything is too much connected, then chaos will happen. Chaos will occur. Mountains will shake so fast that no one will be able to reach the top. Everyone will just keep going around in circles. Between these two, there is a delicate turning point. Kaufman believed that this is the place where life flourishes best. But the difficulty was that his model could not reach that delicate turning point on its own. That is, self-organized. We had to set it by hand. The real fun comes when this system reaches that delicate state on its own, like our sandpile reaches. We were in search of that same magic. Darwin's words are easy to understand, but writing them in math formulas is very difficult. Darwin had thought that everything runs like a straight line. Everything is linear. But our world is non-linear, where even a small action can bring a very frightening and big result. Just as one grain added to the sandpile can make the whole pile fall. Similarly in life, also one small change can change all the beings of the whole world. Darwin had said that in the world, only the one who is strongest will survive, the one who is fittest. The other meaning of this is also that the one who is weakest, the one who is least fit, nature removes them, eliminates them. We made a game-like model on our computer. In this, we chose the weakest being and placed a new being in its place. This new being was completely different. It is very easy to think that the being that is weakest cannot withstand a change in weather or any outside trouble and is the first to be finished. We imagine that many beings are sitting in a large circle. This is just like a food chain. Every being is connected to its two neighbors, like a frog and a fly. The method of working was very simple. Find the being in the circle whose power is the least. Give that being and both its neighbors new numbers. That is, random values. Getting a new number means that those beings have changed. Mutation has happened. This was perhaps the world's simplest model. In it, just some numbers were being changed again and again. But the result that came from this simple work was astounding. When we ran this game again and again, we saw that the average power of beings started increasing. But after some time, the increasing stopped, and the system reached a delicate state. That is, the critical state. Here a chain reaction started. When a weak being changes, its neighbors also change. The neighbors changing can make their next neighbors also weak. In no time, a very big wave of change runs through the whole system. This is what we call a sudden destruction, or punctuated equilibrium. Most of the time, everything remains calm, which is called the period of calm or stasis. But then suddenly an explosion happens, and many beings change together. Big accidents happen at a special pace, but they have no fixed limit, neither in the real world nor in our computer game. Investigating old rocks and bones also gives the same evidence that the development of life, that is, evolution, is part of that delicate turning point of nature. Whenever we talk about great destruction, people think there must be some very big reason behind it, like the Alvarez theory, which says that 60 million years ago, a very big rock fell from the sky and dinosaurs were finished. A big crater in Mexico and a special soil spread across the whole world, iridium, is considered evidence of this. But this way of thinking has two big weaknesses. First, it seems that dinosaurs were already starting to decrease millions of years before that rock fell. When they were already going, blaming the rock doesn't seem right. The real question is, why were they already becoming weak? Second, how did that rock kill the dinosaurs? There is no solid evidence of this. People just estimate that maybe the weather changed. In our delicate state, that is the critical state world, for great destruction there is not always a need for some big push from outside. Nature's own internal work, internal dynamics, is enough. Like the falling of a rock can just be a small beginning, which started a domino effect. Destruction happened because nature was already standing at that delicate turning point. So what is a being, an organism? A thing whose all parts are connected to each other and bound by each other's fate. Our sandpile is also a being, because one grain falling shakes everyone. Our theory proves the Gaia idea to be true. In nature, species, that is, species, don't change separately. Rather, the entire system, the entire ecology, together reaches that delicate turning point. A small accident is just a beginning, but the whole body is put in danger because of that domino game. We are all part of a large meta-organism, a meta-being. In real life, we cannot turn back the wheel of time, but in our simple model, we can do this. History and the evolution of life, that is evolution, rests on small and strange events. We often think, what would have happened if that had not happened? What would have happened if Columbus had left his discovery halfway? What would have happened if someone went into their old life and changed one small thing? Like what happens in the movie Back to the Future, where the stock market will be tomorrow, nobody knows. These unknown things of life are what make stories interesting. If everything in the world were fixed in advance, then stories would be very boring. And if everything were completely crazy, chaotic, then it would also not be understandable. Stories feel good only when the world is in that delicate state, in that criticality where anything can happen. Scientists call this the butterfly effect. This means that a butterfly flapping its wings can also change the weather very far away in the future. Our brain can understand the most tangled up things of the world. So we think it must be very complicated, very complex. But perhaps this is not so. It is possible that the brain also manages itself in a very simple way, like a sandpile. The brain has trillions of neurons that are connected to each other like wires. Our every thought is like a small or big destruction. The brain was not designed by some engineer sitting down. Our DNA also does not have so much information that it can describe every single connection of the brain. The structure of the brain forms on its own as we solve our experiences and difficulties. Why should the brain be in a delicate state? Why should it be in a critical state? If the brain were very slow, everything subcritical, then information would not reach from one corner to another. If the brain were too fast or chaotic, then every small signal would make an explosion in the whole brain, and nothing would be understood. Therefore, the brain has to be at that delicate turning point where it is very sensitive or susceptible to every small piece of information. This very quality of the brain makes it capable of thinking and learning. That is all for this book. We will meet you again in a new episode with a new book. Thank you.